Welcome back to the deep dive. Okay, picture this. You're flying a massive airliner, cruising high at, say, 37,000 feet. And somewhere out there, on the wing, fuel is just pouring out. Silently, you can't see it, you definitely can't hear it over the engines. But your job right then is to find this invisible problem using, well, basically just math. Applied math.
High stakes.
Exactly. And that's what we're digging into today. We're going deep into the standard, absolutely non-negotiable safety procedures. These are drawn from Airbus safety docs, covering everything from the A300 right up to the A380 family. We're looking at how crews are trained to spot, manage, and hopefully contain a really bad in-flight fuel leak.
Yeah.
Because the moment that starts, you've got, what, two massive threats right off the bat?
Immediately. There's the fire risk, fuel spraying onto hot engine parts, maybe later onto hot brakes during landing. That's huge.
Right.
And then there's the ticking clock of fuel starvation. Run out of fuel, you lose engines. It's that simple. It becomes a fight against time, against physics.
And I guess he's against panic, too.
Yeah. Well, that's where the procedure comes in. What's absolutely vital here, especially when fuel is disappearing fast, is that there's just no room for making it up as you go along.
No improvisation.
None. Speed, yes, but speed in following the book, the Quick Reference Handbook, the QRH, that's the playbook. Yeah. Sticking to it step by step is everything.
Okay, so let's start at the beginning, detection.
Yeah.
Because like we said, you usually can't see it at first. So it comes down to the crew being, well, diligent mathematicians almost.
That's a good way to put it.
Standard operating procedures, the SOPs. They mandate these regular fuel checks in crews, right? Like every half hour or maybe over a waypoint?
Correct. Standard practice.
Yeah.
And it involves a couple of key checks, key calculations.
The first one sounds pretty basic, addition versus subtraction.
It is, fundamentally. That's the core test. You take the fuel on board the FOB right now, and you add the total fuel used, the FU, since you pushed back from the gate.
Okay.
That number, that sum, should pretty much match what you started with, the BLOCK fuel amount loaded before the flight.
Makes sense.
So if that sum keeps going down, check after check, and significantly down, well, that's your mathematical proof. Fuel is leaving the aircraft somehow, but it's not being burned by the engines.
That's the smoking gun, mathematically speaking.
Exactly. It points straight to a leak. And, while some newer planes like the A350 might display this calculation for you right on the screen.
Ah, convenient.
Yeah, on the cruise SD page. But for most of the fleet out there, this is still a manual calculation, something that pilots have to physically do themselves. Compare the numbers.
And there's a second check, too, comparing actual fuel with the plan.
Right. You compare the current fuel on board against what the flight management system, the FMS, or maybe your paper computerized flight plan, the CFP, predicted you should have at that point in the flight.
So if there's a growing difference there.
Another big red flag, yeah. If the actual fuel is dropping way below predicted, something's wrong.
Okay, but hang on. If these planes are so advanced, with all the computers, why the reliance on manual math? Why doesn't the plane just, flash a giant leak? Yeah. Warning the instant it happens.
That's a really important point. And the source material we looked at is very clear on this. Those automatic ECAM alerts, you might see something like fuel F, used fall, disagree on an A330, for example. Those are extra safety nets. They're backups. They are absolutely not a replacement for the crew doing those regular manual checks.
Why not? Surely the computer's faster.
Sometimes, but not always early on. The manual checks often provide the very first indication. You might spot a discrepancy manually, maybe half an hour, before the loss rate is high enough or the imbalance is big enough to trigger the automatic system's alert threshold. Early detection is key.
So the human check is the first line of defense.
Absolutely. And crucially, the automated systems themselves have, well, let's call them blind spots. There are basically two types of automatic detection happening. One is a sort of fuel system consistency check, looking at quantities and expected flows upstream of where the fuel gets measured for engine burn.
Right.
The other is specifically engine fuel leak detection. This compares the fuel flow going into the engine versus what the engine computer knows it's burning. This is downstream.
Okay, upstream and downstream. So what's the catch with the engine alert system? Where's the potential gap?
This is where the actual plumbing, the physical pipes, really matters. There's a specific section of fuel hose between the low-pressure shutoff valve and the actual fuel metering valve that feeds the engine.
Right.
If your leak happens right there in that specific bit of plumbing, fuel can be dumping overboard, maybe quite a lot of it.
But the engine computer doesn't see it.
Exactly. because it's happening before the point where the fuel flow going to the engine is accurately measured for that comparison. The engine thinks everything's fine. The only way you'd catch that kind of leak early is with those manual big picture fuel quantity checks, adding up FOB and FU.
Wow. Okay, so diligence with the math is really the primary firewall then. So what happens if the math is screaming leak, but maybe the crew's gut feeling or maybe other indications make them hesitate? Let's look at that A330 case study you mentioned. A night flight, right?
Yes, a classic example, unfortunately. Flight starts normally, block fuel, about 45,600 kilograms. Then at T0 plus 35 minutes, so right on schedule for that first fuel check.
They do the math?
They do the math, and they find a discrepancy of 1,440 kilos.
Yeah.
Almost 1.5 tons of fuel just gone, missing from the equation.
That's huge for just 35 minutes of flight.
It is. But interestingly, the lateral imbalance, the difference between the left and right wing tanks, was tiny at that point, only 90 kilos.
So the wings looked balanced even though fuel was missing overall.
Pretty much. And the captain, according to the report, initially put the 1.4-ton discrepancy down to normal fuel transfers, specifically transfers to the trim tank.
Okay, explain the trim tank again.
It's a smaller tank, usually in the horizontal stabilizer, in the tail. It's used to help manage the aircraft's center of gravity, its balance, especially during cruise. Fuel gets shifted automatically fore and aft to keep the plane efficient.
Right. And how did that mask the problem here?
Well, this is where the plane's own systems, designed for efficiency and stability, actually worked against early detection of the leak itself. On the A330, above flight level 255, the system automatically tries to correct any significant lateral imbalance.
Okay.
So if one wing starts getting lighter because of a leak, the system might automatically transfer fuel from the heavier wing into that trim tank in the tail.
Ah, so instead of the fuel difference showing up clearly between the left and right wing tanks, some of that difference gets shifted aft, hiding the true extent of the wing imbalance.
Exactly. It balanced the symptom, the lateral imbalance, which made the crew initially dismiss the overall fuel loss number. It temporarily hid the severity.
Nasty interaction. And what was the actual cause? Did they find it later?
They did.
Yeah.
Post-flight examination found the root cause was depressingly simple: an incorrect assembly. The mounting flange on the primary fuel hose connecting the pylon to the left engine, it was misaligned, just not put together right.
Just bad maintenance.
Seems like it. And because of that misalignment, fuel was leaking constantly right from the start of the flight, about 45 liters a minute.
Which adds up fast.
Yeah, that's about 2 tons every hour, pouring out.
Okay, so back in the cockpit, 35 minutes in, they noted the issue but didn't act. What happened next?
30 minutes later. So now we're at T0 plus 1 hour and 5 minutes. Time for the next fuel check.
And the numbers are worse.
Much worse. The total discrepancy has now grown to 2,670 kilos missing. And critically, the lateral imbalance is no longer negligible. It shot up to 780 kilos difference between the wings.
Okay, now it's obvious something is really wrong.
Now it's undeniable. So at this point, the crew initiated the formal fuel leak procedure from the QRH.
What's step one?
Step one is basically isolation. You need to figure out which side is leaking. So standard procedure: close the crossfeed valve between the wings and shut off any transfers from the center tank or that trim tank.
So you stop all fuel moving around automatically.
Correct. You force each engine to feed only from its own respective wing tank. That way you can watch the fuel quantity in each wing tank and see which one is dropping faster.
Makes sense. So they do that.
They do that. Then they monitor. 26 minutes later, we're now at T0 plus 1 hour and 31 minutes into the flight. They performed the leak confirmation check required by the procedure, and the imbalance is ballooned. It's now a massive 1,770 kilos difference, heavily skewed to the left side. Confirmed. Left side leak.
Okay, confirmed leak on the left. What does the QRH say now?
The QRH is completely unambiguous at this point. Step 3A, I believe. If a leak is confirmed on one side, the procedure mandates: shut down the affected engine immediately.
Shut down the left engine.
Yes, but the crew didn't. They stopped the procedure right there. They acknowledged the left side leak, but they made the decision to keep the left engine running.
Wow. Okay. Shutting down a running engine, especially over the ocean at night, I mean, that feels like a huge, maybe terrifying step to take based just on fuel calculations. Does the QRH address that hesitation? How does it push crews past that fear?
It pushes them with cold, hard logic and the assessment of risk, primarily the fire risk. The QRH logic is built around confirming the type of leak and mitigating fire.
How so?
Okay, think it through. You've confirmed the leak is on, say, the left side. The QRH says shut down the left engine now. Why? Because that's the crucial diagnostic step. It's the moment of truth.
Okay.
Shut it down. Then you watch the fuel quantity in that left wing tank very closely. If the quantity suddenly stabilizes, if it starts decreasing.
Then the leak must have been in the engine or it's direct plumbing.
Exactly. You've confirmed it's an engine leak. And in that case, the engine stays off. Because keeping it running means fuel is actively leaking onto potentially hot engine parts, maintaining that extremely high risk of fire.
Got it. But what if you shut the engine down and the fuel level in that wing tank keeps dropping?
Then it's not the engine itself. The leak must be somewhere else in the wing structure, the tank itself, the wing plumbing, before the engine pylon maybe. That's defined as a wing leak.
And if it's a wing leak?
Then, and only then, the procedure says you can consider restarting the engine. Because the source of the leak isn't the engine itself, so running it doesn't necessarily increase the fire risk in the same way. Though you still have a leak to manage, obviously.
So that shutdown step is critical for diagnosis and fire prevention.
Absolutely critical.
But in this A330 case, they skipped it, kept the engine running, knowing fuel was pouring out from that side. Essentially, they were gambling against that fire risk.
They were. And interestingly, the automatic ECAM alert, the fuel F use fob disagree, actually triggered about 4 minutes after they'd made the decision not to shut down. So the alert confirmed what they already knew, but it didn't change their course of action.
Then the outcome.
They continued the flight. The aircraft eventually landed safely, but it was 1 hour and 15 minutes after they made that critical decision to deviate from the QRH. By the time they were on the ground, they were missing a total of 5.7 tons of fuel. Huge amount.
And the consequences of ignoring that QRH step, they went beyond just the lost fuel, right?
Yeah.
You mentioned other impacts.
Oh, absolutely. Deviating from a procedure like this often has unforeseen system-wide consequences. In this case, it significantly affected the aircraft's stability.
Yeah.
Remember how they isolated the tanks back in step 1? Closed crossfeed, isolated center, and trim tanks.
Yeah, to pinpoint the leak?
Right. But because they stopped the procedure before potentially confirming a wing leak, which might have allowed reopening some transfers later, they kept that trim tank isolated for the rest of the flight.
Okay, so what did that do?
Well, as the engines burned fuel from the main wing tanks, the aircraft naturally got lighter. Normally, the fuel system would manage the center of gravity, the CG, by shifting fuel around, potentially moving some out of that tail trim tank forward as needed.
But it couldn't because it was isolated.
Precisely. So without that automatic balancing, as fuel burned off from the wings, the overall CG of the aircraft shifted further and further aft towards the tail.
Making the plane less stable.
Exactly. Getting tail-heavy is aerodynamically unstable. By the time they landed, the calculated CG was 39.8%.
How bad is that?
It's getting close to the limit. The red ECAM alert for fuel excess AFP CG triggers at 40.5% on that aircraft. So they were right on the edge of getting a major stability warning.
Wow. So skipping one step in the fuel leak procedure nearly put the plane itself in an unstable state. It shows how interconnected everything is.
It really does. You're not just fighting a leak, you're managing the entire aircraft system. And deviating from the plan can have knock-on effects you might not immediately consider. It's a chain reaction.
That is a critical point. Okay, let's quickly recap the main safety takeaways and maybe some of the final crucial actions required by these procedures.
Sure.
We've clearly established the big risks. Fire is number one, especially with an engine leak, then fuel starvation, obviously, and environmental contamination too, which in the A330 case actually included contaminating the runway because they kept that leaky engine running even after landing during the taxi turn.
Yeah, that was noted in the report. Spilled fuel on the active runway.
Not good. But there's one more really important action right at the end during landing, something about thrust reversers.
Yes, absolutely crucial.
Yeah.
The final step, or one of the final requirements in most fuel leak scenarios handled by the QRH, is a mandatory landing limitation. Thrust reversers must not be used.
Really? But when you've potentially got less fuel, maybe handling issues, wouldn't you want the maximum stopping power from the reversers? Why restrict them?
It comes back to that fire risk. Again, think about what thrust reversers do. They blast engine exhaust and air forward and outward.
Right.
If you still have fuel potentially leaking from the engine nacelle or pylon area, activating the reversers could do two very bad things. One, it could blow that leaking fuel forward onto the brakes, which are going to be extremely hot after landing. Big fire risk right there.
Okay, makes sense.
Two, it could potentially blow fuel vapor or even liquid fuel back into the engine's own air intake. That could cause an engine surge, overheat, or, again, fire. It's just too risky.
So it's a mandatory no reversers landing to contain that fire risk right until the plane is stopped and secured.
Precisely. It's about managing the risk profile down to the absolute last moment.
It all comes back to following the plan.
It really does. The overall conclusion from the safety documentation we reviewed is crystal clear. Strict adherence to the published procedures, the SOPs for detection, the QRH for management is the absolute bedrock of safely handling a fuel leak. The procedure is designed specifically to diagnose the leak type under pressure, isolate it where possible, and above all, minimize that ever-present risk of fire.
So, looking back at everything we've discussed, vigilance through those manual checks is number one. You can't rely solely on the automation.
Correct. Earliest detection is manual.
Then, the step-by-step isolation and confirmation process in the QRH is key to figuring out what is leaking and why shutting down the engine might be necessary.
The diagnostic logic. Yep.
And finally, understanding those less obvious consequences, like the danger of an aft CG shift if you skip steps, or the critical need to avoid thrust reversers on landing, shows just how vital it is to follow that procedure to the absolute letter.
You have to trust the process, even when it feels counterintuitive.
You know, if this deep dive highlights anything, it feels like it's the role of the human pilot, even in these incredibly automated aircraft. They aren't just system managers, they are genuinely the last firewall.
Well put.
That difference between getting home safely and, well, not. It can literally come down to having the discipline, maybe the courage, to follow that QRH precisely. Even when every instinct might be screaming that shutting down a working engine is the absolute last thing you want to do.
That's the challenge, and that's why training and understanding the why behind the procedures is so important. It's not just about managing fuel, it's managing a cascade of potential failures.
A really complex interplay between machinery, physics, and human factors. A perfect thought to end on.
Indeed.
Thank you for joining us for this deep dive. We'll catch you next time.